So good afternoon, everybody. So today I'm going to present what we, Synaptics, are doing in the field of AI on the edge, and how we can accelerate this kind of stuff. So the previous two presentations from Alice, and I don't remember his name, Frédéric, sorry, are actually a very good introduction to what I'm doing. I'm going to present, and this will enable me to skip a few slides because those were already presented. So thanks for that. So this one slide is already presented by Alice and Frédéric. So why edge inferencing is here to stay? Because of the gain in privacy, security, response time, and availability. So nothing more to add. So about Synaptics, we are a semiconductor company, fabless. And you most probably have used one of our products. Closer? Here? Okay. Whatever at home, on your phone, on your laptop, there is a good chance that you use a Synaptics product. So one example is the Swisscom box, the new Swisscom box, which is using a Synaptics chip, the VS550, which has some AI because you can do voice-enabled commands control. You have also the new Google product, the Nest Mini and Nest Wi-Fi, which are using the AS371 chipset from Synaptics. This one already has an NPU. And then the upcoming chip, the VS680, is going to bring a lot more performance. So how do we get faster? First, by designing hardware that can do AI accelerated, so through the usage of neural processing units, NPU. Then, thanks to software development, because in order to use this hardware, you have to do a lot of toolkit development, a lot of drivers, a lot of just-in-time compilation in order to be able to use this kind of NPU. And last but not least, also through the design of a model architecture that will make best use of our NPU architecture. So this slide presents the three chips that we have currently, the three system-on-chip, SoC. The first one that is used in the Swisscom box, the VS550, only has a GPU. So traditionally, acceleration on hardware is using GPU, and this is the main solution, for example, used by NVIDIA product. With the VS550, we are able to do a few hundred of mega operation per second. We have the next in line, the AS371, used by Google product. We are able to do 1 tera operation per second. And this is way enough to do a lot of audio application. With the VS680, which is our new flagship product, and it is actually currently taped out. We have a test chip, and it's being tested right now. We are able to do 6 or even, we hope, better, 7, maybe 8 tera operation per second. So with this kind of hardware, there is a lot of application that you can think of, and we're going to present some. So this slide describes a bit a typical hardware architecture, like the VS680. So you can see that you have a lot of hardware blocks, and all of them are connected through a same bus, the AXI bus, which also connects the main memory, the DDR memory. The NPU has the same access to the same bus as all the other blocks, like the CPU or the GPU or the RAM. So this is a very important point for performance reason, because you want to have a very fast path between hardware blocks. For example, if you have a video coming from the HDMI input, you want, or just the reception of IPTV, you want to be able to access this data in the same speed as other hardware block, like the video display or the GPU. So the NPU is designed around the three major components. The parallel processing unit, which is able to compile, to run programmable code like OpenCL code. We have also the tensor processing unit, which we use for specific layers, which are very important, like fully connected or max pooling or activation functions. And last but not least, the NN core, so the convolution core. Our design enables us to, depending on the power that we want, to have one or more NN core and one or more TP core. And the main thing about the NN core is that it can only execute 8-bit convolution, so integer 8-bit convolution. So the presentation from Frederic explained in details why quantization is really important, and this is how we can speed and low power. So I'm not going to go through that, but basically, in order to produce something that will run optimally on the platform, you need first to import the model, to quantize it to 8 bits, most operation, and then to optimize it so that it can use efficiently one of the other part of the NPU core. So we have two techniques for quantization. The first one, which is the simple one, is post-training quantization. So you take a pre-trained model, floating point 32, and you quantize it after training using a typical data set. And when this typically doesn't degrade the performance, but for some model it can. And in case it degrades the performance, the accuracy, then you would switch to quantization-aware training. You have PyTorch or TensorFlow that can support this kind of training. So this slide presents some popular models like Inception, MobileNet, ResNet, and present the top 5 accuracy that we get using those models, using the quantized version of those models. And as you can see, we don't lose a lot of accuracy. It's very minimal. So as I tried to explain, we have a very powerful programmable hardware. But in order to use this kind of hardware, you need a lot of software. And a lot of development is done at the software level, at the driver level, at the tools level, at the framework level, in order to leverage what we can do on the NPU in conjunction with the CPU and the GPU. So the Synapse framework, which stands for Synaptics, Neural Network and Acceleration Processing, brings some sample application that we, Synaptics, or our customer are interested in. But it also brings drivers. It implements standard library, standard API, like the one defined by Google, the Android NN API. And it can run on various platforms like Android and Linux. Yeah, and last but not least, our Synapse framework includes a component which is called Secure, which is used for the secure inference. So you maybe not know, but ARM subsystem has a way to execute secure code in a trusted way, which is called trust zone. And our architecture enables the secure inference of models, thus protecting data contents from piracy or from basically content that you don't want to publish. So we have two ways to do inferencing on our chipset. The first one is what we call online inference. We basically construct the graph, the binary graph that will execute on NPU dynamically. And we leverage the API that are defined, for example, by Google, the NN API on Android. So this API will communicate with a various hardware abstraction layer that implements a set of AI functions. AI. 7 minutes? Okay. So we still have 5 minutes left. Let's try to go faster. So basically, this implements the AI directly on the edge by supporting common format like TensorFlow Lite or other stuff like Caffe2. And what is important here is that we JIT compile when we do a binary graph generation, you compile just in time the model so that it can run optically. But there are sometimes cases where, for example, the customer doesn't want to publish its model in an open format like TensorFlow, or maybe you also want to run this model in a very secure way, and in this case, you don't want to use online inferencing, you're going to switch to offline inferences. Basically, we generate a binary graph ahead of time, thanks to the Synaptics framework. So we have the toolkit that will take the standard, the model in the standard format, like TensorFlow or NLX, and you will be able to do everything that is needed in order to have something that will run optimally on the device without even any initialization, because all the compilation, all the generation of a graph is done offline on the host. So thanks to this Synaptics framework and the NPU, here's some numbers of some of the model that we support. For example, MobileNet, ResNet, or Inception. So if you compare the same model running on a CPU core running at 1.6 gigahertz compared to what we have on the AS371, the audio chip, we are already 10 times faster. So we can execute MobileNet v2 10 times faster than on the CPU. With the VS680, the new chip, we will be 100 times faster. These slides compare the VS680 performance, speed, with the two edge AI processor, the Google Coral Dev Edge TPU, and the NVIDIA Jetson Nano. So we are able to do this kind of, MobileNet or ResNet or MobileNet SSD in, so faster than those two platforms, while still being lower power and lower cost. So now you're going to tell me, we have all this performance, all these speeds, what we can do with that. So at Synaptics, we are traditionally a multimedia company, like Swisscom. We do support IPTV, set-top box. So one important use case is AI upscaling, because most TV sets are 4K, most TV content are still 2K or less, so we use AI. We are going to use AI for this kind of application. And so these slides, you have, I hope you will see the difference. This is upscaling using a traditional computer vision method that is implemented in hardware. And this is the same pictures upscaled with AI. So you can see around the fur of the bird, or on the skin, this is hardware, this is AI. You can see that the image are much sharper. AI, hardware. same input image. And we're going to do this kind of AI upscaling in real time at 30 frames per second. Also, because we have this available power, we will be able to run multiple models at the same time for various applications like voice control, face recognition, picture quality control, this kind of stuff, all at the same time. And last application I want to talk about is deep night vision. So being able, finish, idiot, being able to see in the dark. And here you can see one of our models running on the VS680. The left picture is the input, so it's very dark. Then you have a scaled input, scaled image. This is what you have typically in cars. The third image is our AI augmented picture, and the fourth image is the ground truth, obtained using long exposure camera. So if you make a zoom, you can see that, the next slide, that the quality you can get using AI is much better than what you can get with traditional computer vision methods. And this is the end of my presentation.
Okay, thank you. Do we have questions from the audience? Yes.
Hi, yeah, thanks for that talk. You showed very impressive numbers for accelerating the inference with your new chip that's coming out. But do you have any estimations yet for power consumption?
Not on those slides, but we are targeting a few watts, basically, for example, even for the most stringent case like AI upscaling, which will use basically most of the NPU, we will be able to run that at a few watts.
Your deep night vision looked quite impressive as well, but I couldn't really tell. You said that you usually have to have a long exposure time in order to capture enough photons from whatever's in the scene. The results that you're showing, is that just to say that you can get a much better image quality overall, and not that you can do it in a shorter span of time, or do you have a clever way of managing to get the actual light data faster than a normal camera can?
No, sorry. On the VX680, we have integrated an image system processor, an image subsystem, which can control a camera. But if we look at this, when I say long exposure, this is not something that you can do in real time because you need something like half a second expose time. So
the scaled input, that comes from long exposure as well?
No, the scale input is using the real-time stuff. So you just take the 8-bit color range, which you scale, basically. When you have, so you look at the chroma of the image, and you will scale where you have data.
Okay, so you still have the fundamental physics limits with the amount of light that the photodiodes can take in.
Exactly,
okay.
And you also upscale. You not only scale the color, but also the noise. That's the issue.
Okay, thank you.
Thank you, Abdel.
Thank you.